Hello, everyone. My name is Anthony Shalakov, and with me is
Leonardo Sabetta.
Bradley McIntire.
We are team number 1106. We are coached by Major Brittany Oletti, and we are from the United States Military Academy in New York. We chose Problem A, Kangaroo Mother Care.
According to the CDC, in the United States, approximately 35 babies die each day neonatally within the first 28 days of birth. A recent review of infant mortality indicates the presence of a wide range of mortality rates in human babies. To better understand the variance in mortality, several studies have been conducted. A meta-analysis of some of the different studies indicates that the direct care of an infant through the use of Kangaroo Mother Care, KMC treatment, can play an important role in the survivability of an infant in its first 28 days of life. The authors of the report recommend that all infants receive care from their mothers within 24 hours of their birth and receive at least 8 hours of contact each day to optimize KMC treatment and survivability. To better understand the situation, we developed a model of the interactions between an infant human baby and its mother under the effects of KMC treatment. Definitions for our research are as follows. Kangaroo Mother Care, KMC, is skin-to-skin contact between a mother and newborn and will be taken as the minimal core component of KMC. Conventional care is motherly care absent of KMC.
We have four initial assumptions. The first assumption is that we assume the birth rate remains constant over time. In reality, birth rates can fluctuate due to various factors. Second, we assume a constant and stable environment without any external influences. Changes in the environment can affect population dynamics. Third, we assume the conventional rate of infant death is always constant. Finally, the benefits of KMC are based on an 8-hour initial value from a study. We extrapolate that this value is only linearly different for longer or shorter KMC session durations.
So to begin our modeling process, we decided to start with a general differential equation. One such general equation is rate in minus rate out, a classic differential equation, where t in our case is the time in days since the birth of an infant, where t equals 0. Y of t is the amount of infants at time t, and the rate in is the initial amount of infants born in a single day in the US, and the rate out is the rate at which infants die per day when 8 hours of KMC is provided. On this slide, we have our rate in, rate out model applied to our scenario. To begin, we started with finding data relevant to this scenario. In particular, according to the CDC, in the United States, there are 10,039 infants born per day, on average. Additionally, according to data found in a meta-analysis that we've previously mentioned in the introduction, there's a 32% reduction in infant mortality when 8 hours of KMC a day is applied during the first 28 days of an infant's life. On the right-hand side of this slide, we see the primary equations for this model. On the top, we have beta minus t squared times beta times alpha omega. Here, beta is the initial amount of infants born in a single day in the United States. Alpha is the rate at which infants die per day when given 8 hours of KMC, and omega is the fitting parameter to account for the linear loss of effectiveness of KMC over 28 days. The fitting parameter is arguably the most important parameter that we have in this set of equations, as a key element of the application of KMC is that the effectiveness of KMC diminishes over time. On the left-hand side, we have a graph of the infant population at time t. Here, we've picked a singular point in time, or any given day, because on average, 10,039 infants are born. We've isolated that day and tracked 28 days from that day. Using the unassisted graph, where we have a constant linear death rate, as mentioned previously in the assumptions, and then we see our assisted graph on the top, which has our main model of 8 hours of KMC applied. Here we can see that the rate of death of the infant population has slowed significantly over time. On this slide, we've made use of the assumption that the rate of death and the rate of KMC can be linearly transformed. Here we've used the disparity between assisted 8-hour KMC rate of death and the unassisted or constant conventional care death rate that is defined as delta alpha. And we've used capital T to signify the amount of time that KMC is given to an infant in hours per day. Here on the left side we have a similar graph to the graph seen previously. However, now it includes what happens if KMC is applied 24 hours per day. Although this top graph may look constant, there is actually a decrease of 22 from the total population if KMC is applied 24 hours per day. On this slide, we have an animation that shows the constant linear death rate titled unassisted, our KMC 8 hours per day death rate previously shown, and KMC varying amounts from 8 hours to 24 hours per day on repeat. This is to show that we can linearly transform the KMC 8-hour death rate seen here. Fortunately, the linear model previously shown does not take into account the effects or impact that KMC has on the mother. So we propose another model, the predator-prey model, a common differential equation model, in order to model the effects on the mother of KMC relative to the baby's health and the mother's health. In this slide, we have our predator-prey model in action in relation to the situation. Here, where y-axis is relative health and the x-axis is time in hours, different from the x-axis on previous graphs, and where 10 is 100% of the relative health and 0 is 0% of the relative health. Here, when we've plotted our graph on the left side, we see that the mother's health is highest when the child's health is lowest, as seen in classic predator-prey models, but also that at the 8-hour mark, the two lines intersect, and this occurs at every 8-hour mark within 24 hours. This suggests that 8 hours is the optimal amount of time for KMC to be applied in daily sessions, and that this should be followed with no less than 8 hours of rest. Here's our lessons learned and limitations of the various models that we've produced throughout this project. First, KMC is best applied at the 8-hour period for no more than 8 hours and quickly after birth. This was seen in our predator-prey model on the previous slide. We've also noticed that this crossover point is at the 8-hour mark, which is why our recommendation is that 8 hours is the optimal amount of time for KMC to be applied, followed by 8 hours of rest in order for the mother's health to recover appropriately in order to perform more KMC on the infant. Additionally, in our primary model, or our first model, we saw that KMC, when applied quickly after birth, is more effective than KMC applied near the end of the neonatal period, which is at the 28th day. Some other various limitations are that we assume a stable environment, where there are no other death factors considered such as sickness or disease, and the conventional rate of infant death and birth is constant. We also could not show the effect of KMC on the mother in the same model as the infant population over time.
To advance our research in the future, modeling could be done on both the effectiveness of kangaroo mother care over time in the same model as the impact on the mother. Additionally, research could be performed for varying amounts of kangaroo mother care, monitoring the baby's vitals as well as mothers quantitatively.
These are our citations. Thank you so much for watching.